What can I point?
I don't know.
Someone has issues with
someone
is missed it, so then we can already start going.
Oh, yeah. Shit, I forgot.
That's right, but I think it's.
Did anyone still have trouble downloading the data set? If yes, please raise your hand. We have some, USB drives to distribute the data before we start.
Yeah, that was my job in the beginning, I forgot. Gibt's das überhaupt? Gibt's das überhaupt mit dem Pointer?
So, was there anyone else who needed data?
So, da meinst du. Ist das nicht da? Jetzt sind so alle. Das hier weg. Das ist ein Unterschied. Also. Was ist da? Pink, magenta. So, oh, größer.
Okay.
Touch indicator. Geht das? Schon.
Okay.
Nice. Presentation? Ja, ich glaube nicht. Presentation Mode? Oder?
Ja.
Da, aber von der Seite.
Ja. Okay. Anybody still missing the data set for his group? No? Okay. So before we start, I still want to stress again, we have uploaded the results that we get out of MZmine and that we use for the next tools and the next workshops for every group. And they are on the GitHub repository. We will probably send a link around in the evening as well. So for tomorrow, you download the results that we have on the GitHub. So everybody's on the same page, because all the other tools and the workshops, they depend on that everybody has the same output. Today, we will still go through MZmine and analyze and optimize everything. And if you have any questions during the workshop, please raise your hands. We have Robin and probably Corinna going around and helping you guys. And if you feel that you get lost, please just like scream, stop, and I will like take my time, reiterate. It's really about you getting a grasp of the software to know how it works, and that afterwards you can do the analysis on your own. And in the end, after the hands-on session, you still have time to redo the analysis, and then all three of us will be able to go around and help you going through everything. So a quick checklist. So everybody should have the data set. You should have the spectral library that you downloaded. And yeah, you should have the MZmine software. And depending on if you downloaded the portable or the installer version, either with the portable version, you can just start it, and with the installer version, of course, as well. But you should have two different files here. Maybe one is called MZmine and one is called MZmine_console. It doesn't matter which one you run, just the console looks like you're a hacker. So if you want to look like a hacker, you can use it. We can, it doesn't matter which one, you can just start any one, and maybe on the first start, it takes a bit longer, and you will probably get a pop-up up here in the right corner. And if you haven't used MZmine before. And of course, I don't get the pop-up on this laptop now, but the pop-up is questioning you to where it can store some temporary files, because during the processing, we get some results, we get some intermediate results, we need to store them and load them back and forth during the processing step. And it's important that we, if we, for example, don't have too much space on one hard drive, we set it to a hard drive where we have enough space. and probably also that it's a fast hard drive. So I'm going to reproduce what we have to do with it. So usually you can click on the change button in the top right corner, and I'll go to the same setting. So the dialog you get should look something like this when you click on the change button, right? You have the temporary file directory, and you have the 3 dots in the top right corner.
Maybe we have to pull down the window a little bit because it's well, this one because it's too high. The projector is too high.
Yeah.
And maybe restart will get the yeah, I think like that.
Yeah.
Yeah, that should work.
Okay.
It's perfect. Nice.
Yeah, so if you have the pop-up up here, you can say, okay, I want to change the temporary file directory. If you don't have that pop-up anymore, you probably set it already. Then you can reach that by clicking on project and set preferences. We also have a shortcut for that. So if you want, you can just press Control P. Everybody okay? And when we open that window, the dialog by default looks like this. If you click on the, just on the change button, you get a filtered version already. And if you want, you can just, on the top here in the search bar, I hope everybody can see the mouse. We changed it, so you can just type temp, and then you get the temporary file directory. And usually we just, you can click on the 3 dots here on the side. And then you can select any folder where you have enough space. So for example, on this computer, there are still 144 gigabytes free. That's not too much, but yeah, it should be totally fine for today. So, and we just create one folder on a D hard drive to store the temporary files. You can call it anything you want. We just call it MZmine temp, so we know what's in there. And yeah, so if I wanted to create a new folder, I just press create a new folder, and then I set the folder name to MZmine, and I'll just call it temp2. So, and select this folder, and then this one in here should update. Everybody okay? It's good to see some notes. And afterwards, you can press OK. And yeah, I hope everybody in the audience, can you read the menus? Is it big enough? Good. And okay, so first of all, the interface of MZmine. In the middle, you just have like some welcome tab, and you can find the publication. You can find some short tutorials on YouTube, and you can also find the documentation for MZmine. So by now, most of the modules also have an online documentation. So if you're not at a workshop and you want to know how something works, how to set it up, you can just click on that link, and you should open the MZmine online documentation. And for example, I can then here just search anything and find how to use, for example, the module ADAP chromatogram builder. And now we can also see that on the left side here, we have a tab that's called the MS data files. We have the feature lists and the libraries tab. And now during the processing, we will basically import some data files. Then we process them, get some feature lists, and in the end, we can match them to spectral libraries. So now to import the data, they are the easiest way. Yeah. Okay, I was just about to ask. So to import data, there's several ways. We can either just, if we have the folder open somewhere else, we can drag and drop it in here. But since this is my laptop, I don't know where the files are. You can also just say raw data methods, raw data import, and import MS data. So in the top menu, yeah, that's visible. And again, for like the most used stuff, there are some shortcuts. And when you press on this menu icon, you can then open yeah, the import dialog. And yeah, what you can do here is I'll just go to the folder so I can show you the different ways. So what I could do if yeah, I didn't have this dialog, you don't have to follow along everything. I just want to demonstrate. Oops. You can just select some files and drag and drop them, and then MZmine will start importing them. And for the sake of yeah, demonstrating this, I would say we yeah, select some different files from our data sets. So every data set should have, I think, the blood samples, and then either, I think, upper back or forehead or something. No, was it forehead?
Different skin swaps.
Yeah, different skin swaps. And so what I would recommend is that we import some of the yeah, the blood samples and some of the skin swap samples. And yeah, so no, not at the moment. We don't want to import everything. We just want to import a subset. So if you import everything, then it will probably take a longer time. So for example, I'll show you how I would actually now select which files I import. So when we go from the raw data methods, raw data import and MS data import, I just yes, for example, if you already started importing, then you at the bottom here, there are 0 tasks for me, but for you, you probably have some tasks already. You can right click and then cancel all tasks. And yeah, so how would I select the files that we import now? So in the import dialog, I can just say, okay, I want to select some files now. I navigate then to the location where the files are stored. And I would probably yeah, takes like 3 samples of yeah, the blood samples and say open. Then they are added here. And I can also, again, just yeah, take some skin samples. Does it not? Okay, if it doesn't work, then we just, when we come from the select files dialog, we can just drag and drop them here as well and just close the dialog, because that works. Okay. Everybody has like 6, 7 files or so in the import dialog here. If not, please raise your hand. We have
If
yeah.
we jumped the gun a little bit and imported all of them, should we get rid of some of them, or is it okay to keep them?
It's okay to keep them, but for example, after the importing, you can like remove some files or so. If you're not done importing it, you can just click cancel in the bottom. As down here at the 0 tasks, you can say right click and cancel.
I think the easiest might be to either just yeah, remove some files. So you just select them, right click, remove, or there's project, clear project, I think, right? Or new project. What is it in the project? That you see?
What?
Project and then clear project or something?
Close
or
project.
Close project, okay. So Control Shift Q or like close project, you can just have a fresh start if you imported too many files. It's only for optimization, right? So for optimization, it's going to be nice to kind of run fast. So you do some like sampling of your samples and like 4 blood, 4 skin, something like that. And then it's much easier to kind of look at distribution of data and so on.
Okay. Everybody has some files imported and is able to work at the moment, or is the laptop struggling or so? Do I have to wait? No one says stop, so I'll continue. So now we have the files import. Yeah. Do you need any help or? Okay.
We're just
Yeah. We can compare like the same samples, other samples, but it's good to have like overview of the different sample sizes. So we compare them like for the and I would take my parameters. Yeah, two is so yeah, I think it's the goal we use it to stabilize things and which are also overall and that's why we want depends on your study. So yeah, of course if you want but here that's like the goal of the study was with
Okay, so first thing is really like this workshop is hands-on, so it's going to also take a bit longer than maybe some people want to expect, but it's always the case because there's so many people that need to follow along. We don't want to lose anyone, right? And you can go on. There was just one interesting question about like MZML and MZXML. There's not much of a difference. It's just MZML is like the more recent data standard. Yeah, so it covers more of the metadata. And if you, if you have some new data, I would always convert it to MZML, basically. It's mostly, some people had some issues and we're going to look into that, but it's mostly like a converter that you use in the centroiding. This is what I would say is like the most crucial point. Like MZmL is the newest format that we have so far that most people use. But then the converter, there was some problem with misconvert at some point where like we wanted to use the vendor algorithm for centroiding. It's like Thermo supplies their own and so on. And then if the step was not the first one in the line, it would just use the maximum. Yeah, it would just use a different algorithm that you did not select. Yeah, so there was kind of like a bug in the software with like title maker being first and then mass detection. Centroiding, yeah. So it's just something to maybe look into. But in MZmine, if you drop the files in there, it's going to tell you that there's some zero intensity signals. And if you got that for your data, and you still have the raw data, just reconvert with like the latest versions where everything is fixed. Yeah, so it's been there like a long, long time actually. Just to know.
Yeah.
all right.
Okay. Everybody okay? Does anyone still need assistance or so? Okay, so now we have imported some files. You should in the MS data file section on the left here, you should see the names of your files. And what we can do now is first of all just look how the actual data is represented. So for example, we can get an overview by double clicking on one file. Depending on like how much we waited now, it might take a bit longer or a bit shorter. Do you think I should increase the chart label size a bit? No? Okay, you say so.
Unless someone wants to.
I'll increase it a bit. So what I'm doing now, you don't have to do. It's just for better readability. So yeah, at least it's a bit bigger now. So what do we see when we double click? This is the raw data overview in MZmine. And you get it by double clicking on one file here in the on the left. And what it is, it's an interactive visualizer to quickly look into some of the data that you have. So on the left side here, we by default have the base peak chromatogram. So this just plots the intensity of the highest or the most intense signal in every scan. So it gives you a rough overview how your chromatography looked like. And when we click in here, we can, for example, select this time point, and then on the right over here, we get the spectrum at that retention time. And as I said, these charts are all interactive. So, for example, we could zoom in to the signal here, and we can do that by, for example, either dragging a box, and then we zoom in. And if we want to zoom out again, we can double click on the x-axis, for example, then the x-axis zooms out. And we can also, when we zoom in here, I'll just do that again. When we are zoomed in, we can click on the axis and move the plot left to right. And the same works with the y-axis. And again, to go back out, you can just double click on the x-axis. So when I click around in the chromatogram plot, I can, for example, already see, okay, here, for example, we have one compound at master charge 163 that is here at in my sample. You probably won't find it in your sample. You can find it here at a retention time 3, and you can also find it later on at a retention time 5 or so. So it has the same mass, but it's probably not the same compound. That's something that we have to keep in mind. There might be multiple mass to charge ratios or the same mass to charge ratio at multiple time points in our chromatogram. And of course, we can't just zoom around in here. We can also look at the scan on the right side. So when we look at the scan at that retention time, we can also move it around. We can also zoom in. And if we were to select a signal in the scan, so the selecting, you it's the best to just click on the top of the peak. And then MZmine will start plotting that signal instead of the one you had currently selected. So here we can now see, okay, as the signal wasn't as intense as the 163 here, the chromatogram also looks different. And we could also go to this mass to charge ratio to investigate that. So for example, if you have like some quality compounds and you just quickly want to see, okay, are they detected? They should be in every sample. Then you can do it like this. And then what we can also check is what to do with multiple compounds. So for multiple samples, did we have a stable chromatography across multiple samples? So for that, we can just select multiple files with control. And then say also, how does right click and show raw data overview. And then we open another raw data overview. and we have multiple samples now displayed here in the color that they have here on the left side. So yeah. Yes, but yeah. So the question was if you can also do a manual integration, and it's possible to do that. But right now we are just looking at the data. This is completely the raw data. MZmine is not integrating anything at the moment. No. So we will do some processing. So now we're just looking at the raw data and checking if the raw data is okay. And later on, we will produce the feature lists. And in there, when you don't find your signal, then you can do some manual integration as well. For example, you can make it longer, shorter, add something, and stuff like that. But most of the time, then if you don't find something, or if you lose something along the way, then it's probably better to adapt the parameters. Because if you lose that compound that you're looking for, you're probably also losing a lot of other compounds. So yeah. And now for multiple compounds, we still get the same plot over here. We can, for example, zoom in, and when we select any signal, we would want to see that the retention time here is more or less stable. Yeah, I didn't want to overcomplicate it before. So for example, when we are, what Robin mentioned, we have the raw data overview is mentioned, or like is listed up here, and there's a checkbox. And some of you might already be wondering, why is that checkbox there? So if I don't want to look at only these 3 samples, but I also want to look at 4 samples, what I could either do is open a new raw data overview, or select all the 4 files and make a check mark here. And now you can see that we also have the pink trace in here. And now MZmine will update the overview with the selection that you currently have. So for example, if I was now to just select 1 file again, all the other files will be removed, and we will just have this 1 file. And for me, since I just looked at the skin samples for now, I can also look at the blood samples if they look fine as well. So I can select these 3 files, and then also here look at the stability of the chromatography, and investigate some individual spectra. For example, if I was looking for my reference compounds or so on. Yeah. So anybody got questions so far? No? Okay. It's the, so when you don't select the checkbox up here, then it doesn't update. And if you select the checkbox, then it will automatically update with your selection.
That's also a general thing. Like, you see that checkbox is fried up, and it's just kind of adjust to the selection of raw data files, or maybe even featureless if made for the featureless.
Yeah. And so how would we actually, if we want to check, okay, our chromatography, how good is it? We can then select some of the files here. We can see, okay, here at 3 minutes, there's mainly just like 1 scan shift between the first signal here, so that looks pretty good. And we can also check it at another time point later on in the chromatography. And here it's basically the same story. The signal is a bit more unstable, but basically, the chromatography was good across most of the sample runs. And then I guess we go to what was mentioned yesterday, because we said, okay, how do the acquisitions, or like how do we get the most of our data? We get the most of our data when our MS2 acquisition works well and we don't fragment the same compounds over and over again. For example, like some masses that are in the eluent and elute all the time. So how would we do that, and how would we check how our instrument selected the MS2 files? We can in the visualizations menu. When you click it, we have the raw data summary. So in the top here, you go to visualization. Oops. Right click. Okay. Yeah. You can go to visualization, or you can right click on the sample. I guess it's the same. It will lead you to the same thing. So I'll just do this one now. I right click on the sample, and there's this show raw data summary. Did everybody find it? Okay. And I'll open it.
File summary?
Yeah, sorry. It's the show raw data summary, not show file summary. Yeah, maybe we should do something about the naming there. So it should be at the second one from the top, show raw data summary.
I don't have it on. So I am releasing raw data.
Do you have version 3.9?
No. Because it's
Okay, so maybe you have it. Which version do you have?
I can see.
Oh, that's yeah. Then you probably don't have that feature in there. So does anybody else still run an old MZmine version and does not have this overview? Then just pay attention to what I'll show you. So when I open the raw data summary, I get this dialog, and basically you can just leave everything as it is on the defaults. So yeah, this one is set to MS level 1, and it's set to the raw data. And now we can just open this dialog by clicking on OK. And then MZmine in the background will prepare such a plot. And you saw this plot or similar plots yesterday. So on the y-axis, we have the precursor MZ. You can also see it down here. And on the x-axis, we have the retention time. So what we don't want to see is like constant lines going across from the start of the retention time to the end of the retention time with the same mass to charge ratio. Because that just means, okay, we basically fragmented a compound that was just in our eluent, and we wasted a lot of time. And what we do want to see is like such a nice wide distribution over here. So here the exclusion worked, but we can also see that down here in the end, when there were probably most of our interesting compounds we have already had eluted from the column, that here the instrument didn't have anything to fragment, and then it started fragmenting probably some plasticizers or so in here. There was a question.
So if you had dynamic exclusion on like a 20 seconds exclusion, would you see these straight line of dot?
Then it so it depends on how complex the sample is, right? So if that's the only thing that is at that moment across the intensity cutoff for the instrument to acquire the MS2s, then it will probably look like this one here. So here the sample was like pretty much eluted from the column. It was just like probably this plasticizer left. And you have like every 0.3 minutes or so, you have the same compound fragmented. But I would say this, in here, this is totally okay, because probably the chromatogram was empty by then. So all the interesting stuff left, because the interesting compounds were eluting in the lower retention time range. And here we have a nice wide distribution, like a lot of different MZs were fragmented, and we don't have like, I don't know, 10 spectra of the same compound. This is basically just the intensity of the precursor ion. So the darker the color is, the more intense the precursor was. So it's on the Z, like the color is the Z-axis. So here it's the precursor intensity. You could also select something different there, but yeah, this is basically the default setting, and it gives you, okay, yeah, most of my compounds were of a similar intensity. Some were higher and more intense or less intense or so. Yeah.
If you would see this in all sample types, would you consider changing the gradient to spread out the closely diluting compounds a bit more towards the back? Probably get better PDA.
Yeah, so the question was if it looks like this in all sample types, if we should elongate the gradient. I guess it depends on the coverage you want, because if you need more time to elute everything to get better coverage, you have your analysis just needs way longer. And yeah, it depends on the study size. How much time do you have? How much instrument time can you get? It's always an optimization. So you want like good MS1 shapes. You can do the feature finding. You want good MS2 spectra, and you want, of course, short analysis time, so you can run as much samples as possible. So I would say it's not a problem that the back here is empty, because the column needs to be flushed anyway. So yeah, that's normal. I would say that yeah, it looks like this in the back, because yeah, if we didn't flush the column, then we wouldn't have reproducible chromatography in the end.
Maybe also one thing, because about the chromatography length, of course, there's always a trade-off, and time is the most promising one, right? You need to get all the samples measured in some timing that you have. Some people do like the longer gradients, because then they have more time to acquire MS2 scans and also have like enough data points, but then also you stretch out the shape a little more, so it also gets a bit more narrow, not so high. And some people also have like a dual injection system, so they basically have two columns running at the same time, and then when one flushes, the other one is being injected, and so then you typically don't acquire the rest of the chromatin here. Yeah, so like after maybe like 9 minutes or something, there was mostly just like flushing down, and I personally would not even consider that during data analysis, but maybe it's nice to still acquire the data, because then you can troubleshoot, and you might be seeing some weird pressure profiles. You might be seeing some, you know, like some weird things happening later on. But yeah, with the dual injection systems, for example, you just cut down like at the end of the chromatogram, and you get the next sample injected earlier. Yeah, so you get the full runtime.
You mean what about the patterns on the y-axis? So for example, like this one probably is I would guess some yeah, polymer that just yeah, keeps getting bigger, but that's like probably just like some contamination from yeah, the sample yeah, sample walk-up. And most of the time you can't really get rid of those, so you could add them to an exclusion list. The same goes for this one. If you were still seeing like a lot of compounds that were eluting in the later time range here while the column was flushing, then you could set a static exclusion list for yeah, the plasticizer that we're observing here. But usually on the y-axis, I wouldn't say that there's or at least I'm not aware of like some specific patterns that I wouldn't want to see.
Yes. I think sometimes we might be seeing like the same compound eluting, and then there's like multiple different ions of the same compound at the same retention time. So that's something that we're going to look at more in detail once we do the processing. And you can, you know, like at home, maybe rather, you can play around and you can change all those things. You can see like the precursor MC and the product ions, and kind of see like the same fragments being produced. So you can switch around the plot. But we're not going to show it here. So I think it's a nice plot to play around with, and it's dynamic. But this is mostly to just see that it's like a DDA method, and it also worked. Yeah, so that we kind of have some sanity check on our data. Okay.
That's okay. In the process that you said for this data summary, the date is scan filter that you said that we did not need to do anything.
Yeah.
What is
it doing? Yeah.
So
So the question was,
Remove the scan filter and keep the
yeah,
graph.
yeah,
So yeah, the question was like, there's a scan filter that we did not really touch in the parameters. And so far it was set to only give us MS1 spectra. And it should usually just be for the other tabs. So there's the MZ and noise and intensity tab. We can look at the distribution of our data. Yeah, so we can look at like, okay, what is the distribution, like the accuracy and reproducibility of measuring the same mass to charge ratio? What is like the intensity range that we see in our data set? And so that's usually why we have those filters there. And in MZmine, you're going to see there's a lot of parameters, and it's kind of annoying sometimes because you kind of have to know which ones to set, which ones not to touch. But we try to give some sensible like defaults in the beginning. And yeah, so sometimes just try out. So maybe I would say like we keep some of the questions for later. So there's still going to be more time, of course, during the break also, right? Discuss and get some more questions. And then as we have a break at 11, there's more optimization and so on coming afterwards. And then later, there's also time for you to really go through the software, kind of apply what you learn. And then if there's like interesting things that come up and also things that you want to discuss, we can discuss it here in like a whole audience ship. All right.
Okay, so yeah, Robin was already talking about the other tabs, and I don't want to talk about them too much, but I still want to show you yeah, what they contain and what you can see there. So if you go to the mass over charge tab here, which is the second one, we can basically see the distribution, how much a single mass to charge ratio was detected in our chromatography. And so what we see is a histogram plot. We have the mass to charge ratio on the x-axis, and we have the number of detections that this particular mass to charge ratio was detected on the y-axis. And what we usually use this plot for is we can just quickly check, for example, how stable the mass accuracy was of one chromatographic run. So what I would do is check like a signal that was detected a lot of the time. So I will just use this one here, and I will start zooming in on it. And so I ended up at 388. And what we want here is that we have a lot of detections for that individual mass to charge ratio. So basically here we want to see one of the contaminants or something that is eluting all the time. And now we have to go down here into the settings, into the histogram, and basically just decrease this binning width a little bit. So, and then we get a finer distribution, and we if we zoom in even more, we should see something like this. And what we can see here is that the mass to charge ratio 388 was pretty stable and has a pretty narrow distribution. So we can see that our instrument, for example, didn't shift along the chromatography or so. So sometimes you might get an MZ drift if the temperature changes or so, and you have TOF or so. And but here it looks pretty good. And we have a pretty narrow MZ range. I wouldn't like totally say, okay, if it's narrow, it's good, and if it's wide, it's bad. It totally depends on the instrument. You need to check for example, for some runs that you know that these were good, and this is how the histograms should look like. And then if you start seeing changes, then you can, for example, say, okay, maybe something went wrong here, and I should look into what happened.
And I think also like these two plots actually, it's like MZ and also masked effect. They can also just give you an idea if someone sends you data and you have no clue about the data set, they just said they measured whatever samples. You can kind of see if it makes sense and what kind of mass range were they measuring. Yeah, so maybe they are looking into lipids, and lipids are very saturated, right? So the mass effect can go higher. And you're going to see a very different distribution of MZs and mass effect for different compound classes. Yeah, it's just like a rough overview.
Yeah. Yeah. So from here, I think we can start going into the processing wizard. So if you how many of you have used MZmine before, and maybe even used, or like who used MZmine 2 in his life? Okay. You probably know how complicated MZmine 2 was and how much individual parameters you have to set. Who used MZmine 3? Okay, and who has used the wizard yet? That's definitely not everybody who has used MZmine 3 has used the wizard. So that's good, because then we can actually show you something new here. So on the top in the menu, we have an item called the processing wizard. And you can either open it by just clicking on the menu, or you can press Ctrl W. And then you should see a tab that looks like this. And what do we see here? So down here, there's a depiction of our instrumental setup that we use to acquire some data. And you, of course, might not have an Orbitrap, you might not have an HPL, or you might not have run a reverse phase HPLC. For example, you did a Helix acquisition, then you can just change this column or change this sample introduction mode here to Helix. Or, for example, you did GC, then you can change it to GC, and so on and so on. We even have some settings for Maldi. And basically, this wizard gives you some reasonable presets that, in our experience, will give you for most of the applications will give you some results. We don't say, okay, these are the perfect results, and you can just go with this. You should definitely look into the data. Every data set is different, but most of the time you get something and you can start optimizing that for your specific data set. And which makes working with MZmine a lot easier than it was with MZmine 2 or MZmine 3 without the wizard. So for example, what could these presets look like? If I down here go to the HPLC tab, and instead of HPLC, I say, okay, we didn't do HPLC at like, I don't know, 200 bars or so, but we did HPLC with higher flow rates and higher pressures. So we probably get narrower peaks. You might down here see the approximate feature full width half maximum. As soon as I select the UHPLC, this one changes and gives you another preset. So again, this is a preset. We're not saying it's perfect, but it's way less parameters that you have to set throughout the analysis, because some of them were even repetitive. And so this should simplify it a lot. Then again, on the next page, we have some parameters for the Orbitrap, so our mass analyzer. In here, we can select the ion mode that we use, because most of the time, some instruments are better in positive mode, some are better in negative mode. When we change it, due to the newest changes, the presets for positive and negative mode are the same. But there might be the case that you have some different presets for positive ion mode and negative ion mode. And one nice thing is that later on you can even save the preset. So if you know, okay, this column, this HPLC method, this analyzer method, they always work well with this presets. You can save them and you can load them later on. And then we don't just have presets for Orbitraps, we also have presets for the QTOFs, and we have some presets for FTICR. And we also have presets for low-res instruments. So for example, if you're have a triple quad but are still doing full scan or have an ion trap or so, then you could use that preset. In our data set, it was acquired on an Orbitrap. So we can just select the Orbitrap up here. And in the end, MZmine also gives us choice for the workflow that we are doing. So let's look at the choices quickly, and then I can go through what they actually mean. So we have the choice between a DDA, a DIA, and a library generation workflow. And DDA is a data-dependent acquisition. So we fragment the most intense precursors. We generate fragmentation patterns, and we want to use them to identify compounds and maybe do molecular networking afterwards, or analyze our samples that way. And in data-independent acquisition, this feature is kind of new. There you basically fragment everything, and you switch between low collision energies and high collision energies, and then you have to generate the fragmentation spectra, for example, from the elution profile. And this feature is new in MZmine. If you use it, please let us know how it works and what your experience is with it. And for example, Robin already touched on it. So if you want to make your data public and you have some reference compounds and you feel like that other people could use it, or maybe you should just do it anyway. Someone will probably be able to use it and will be happy that it's there. You can also generate a library if you have a list of compounds that are in your analysis, and then MZmine can do most of the work to export everything to a library that you can just upload somewhere, and then everybody can use it. Yeah. So what we are doing is the data-dependent acquisition workflow. And we ran DDA analysis on all our samples. We want to identify, first of all, we want to hopefully see diphenhydramine, which was given to the subjects, and we hopefully also want to see the metabolites of it. And to do that, we want to do spectral library matching, we want to do statistics, and we want to do molecular networking, and that is all covered in the DDA workflow. Okay, so should we just run it with default settings in the first place, and then
let's load it and then go to I will load the presets and then
okay. So what we have had here, so Robin, you don't have this. I will load the presets that we generated for the workshop, and then we will go through how we actually set them, and how you can derive these presets and these parameters that we set them from the visualizers I just showed you. And I don't know, should we maybe do a break before so everybody can digest? I don't know what the timing is.
I think maybe we just go through, set all the parameters, and then, so break is going to be in 20 minutes.
Okay.
But as soon as we click run, we could basically do a break, forget what we did, and then come back and
okay.
remember.
Yeah. So let's do it like that. So we generated this preset, and in here we have the data to import. You can basically you can select the same files, you can select any other files than we just used. And the more important stuff here is the UHPLC parameters. So the setup was UHPLC, so we have pretty narrow peaks, and so we start with this preset. And let's go through the analysis. So during the processing, we select that we want to apply smoothing. That's the default, and unless you have like really few signals per peak, most of the time you would want to enable it. And the same goes for the stable ionization. So this just means, okay, I use the same mobile phase, so same, for example, water and acetonitrile with the same buffer across all the analysis. So most of the time, you don't want to, change the first two parameters. If you do something, special, and okay, I wanted to see some adducts or something else, then you might want to disable them. But for our case and most other regular metabolomics workflows, just leave them enabled. And you might be able to see that the crop retention time has changed from the default parameters. And why did we change it? So let's go back into the raw data overview. I'll just select a single skin sample here. And by double clicking on it, we get back to this raw data overview. So let's look into the chromatogram here. So I just zoomed in a little bit on the y-axis. And I hope I'm not getting too fast, so I'll wait a little second. Does everybody have the raw data overview opened, or is it processing for someone? Then I just wait a second.
You can go ahead.
Okay. We said that in the wizard, we want to crop from 0.4 to 0.9 minutes. So basically, what do we do during the cropping? We say, okay, between these two times, that's where the important stuff for our study is. And the other one is just, for example, re-equilibrating and washing the column and getting all the dirt out of the system. So so 0.4 minutes is down here in the front. So we get our injection peak where everything elutes, that doesn't have any retention on the column. And we know that our compounds are here at least polar enough to show some retention. So everything that comes down here, for example, salts and clusters and everything, they just rush through the column and they are not important to us. So we can say, okay, we don't use them for the processing. And on the other side, we said that we wanted to stop with the feature extraction at 9 minutes. And when we look into the chromatogram here, we can see that before we get still some signals, which are probably just plasticizers or PEG or something. And after 9 minutes, the column is just washing. And then probably here at 10.2 minutes or so, we start re-equilibrating it back to our default conditions. So that from 9 minutes on, nothing that is of importance to us is still eluting. And also the signals in the back here, even though it's pretty intense, that's just because you're changing completely the composition of the mobile phase. You still get some signal, but it's not important. And we don't need to do that for the feature extraction. So in here, we could then say, okay, we want to go from 0.4 to 9 minutes, and the rest will be discarded. Any questions? Okay. Then the maximum number of peaks in a chromatogram. I think this is still the default. I still want to explain what it is. So basically, it's telling us, okay, how much signals could we distribute for one mass to charge ratio across the chromatogram. And the higher you set it, the more slack and loose the feature detection parameters will become. So it's unlikely that you will have thousands of signals for the same mass to charge ratio. But if you tell MZmine to look for that, it will start looking for that. And then, you might get more noise annotated. So the thing is, I already saw, for example, this like this compound here, where we definitely have 4 signals. So it's always good to not just say, okay, we only get this compound or this mass to charge ratio once. So leaving it with the default, it will give you appropriate results most of the time. If you, for example, have really a lot of isomers and for example, like some branched fatty acids or so, you might want to increase that value. if yeah, most of the time you don't need to decrease it. Yeah.
I'm assuming it takes the 15 most, the MZ features with the most counts, right?
It's complicated. So the question was if we just use the 15 most intense features for one master charge ratio. That's not the case. It's more like how we derive, it's more like a measure of us to derive some parameters internally, because the actual thing that does the splitting of the chromatograms has like, I don't know, 7, 8 or 9 parameters or so. And then we just use this 15 to derive like 2 or 3 of them. So it's more like yeah, something for us to say, okay, yeah, we use this as input. You still might get 16, you might get just 10 or so.
Yeah, it's no like absolute cutoff. It's
Yeah.
really like just saying like, okay, how many features with like a full width half maximum that we set? How many of those features could be in like a chromatogram? And because we use LC, we don't expect like the same MZ across the whole 9 minutes, right? Typically, it's just in like one narrow window moving along. And for GC AE, where we have like all ion fragmentation, we have the small fragments. They're coming like everywhere, right? They're like all over the same, like the chromatogram, we have the same small fragments because of all ion fragmentation. And that's why when you change to GC, there's no such parameter, because we already know that it's not going to be the case, at least for GCA. Yeah. But typically you don't have to touch it, this parameter, only if you have a lot of isomers and similar disease.
Yeah. The next thing is the minimum consecutive scans. So this means how many data points should be there to describe a single feature in retention time dimension. So on each chromatogram, or on each peak in a chromatogram, I'll just pick something here. How many data points do we have there? And so we start at the bottom, then it's 1, 2, 3, 4, 5, 6, and I think there's another one in the back here. If we zoom in a bit, yeah, so there's let's say between 4 and 7 data points in this data set. If you have, for example, longer acquisition times, you might want to decrease that value, or if you have a lot of MS2 scans. So if you're not doing just, for example, top 3, and your cycle time to do the next MS1 is, let's say, too long, let's say it's like 2 seconds or so, and your peaks are only 3 seconds, then you only get 3 signals or so per peak, then you would want to decrease that. But one thing to stress here is that the feature detections, they work better when you have more data points on the chromatographic peak. So I guess the a rough value that at least I personally aim for when I do some acquisitions is to have at least 5 points per individual signal. No. And if you, for example, want to do some quantification in the end, then it's probably better to have even more points, because then you're more accurate. If you're doing, want to identify stuff and you're not working quantitatively, then you can, acquire less points but get more MS2s. So that's how you derive the minimum number of scans. You can also, for example, not only look at the most intense signals, but let's just say I go into this spectrum here, and I just also select an isotope of one of the more intense ones, and we can also see that number of 5 data points should be enough for this one. When I select another mass to charge ratio, this is probably all some adducts of the same compound, so I'll go to some other MZ. Maybe just this one. Yeah, so also for this one, we have 1, 2, 3, 4, 5, and 6 data points. So with 5, we're good. But I would also say that this is pretty strict, because we don't want to generate a huge list of files later on for the other tools. So for this data set, I would say 5 is more strict. You could think about loosening it a bit if you wanted to. So the approximate feature full width half maximum. What is it? So the full width half maximum is the full width at the half maximum of a chromatographic signal. So we can also judge that from the processing wizard. So let's just say we take a signal that's not super intense, and we say, okay, the half height is, or half height is, let's say, rough about here. And it's from 2.58 to 2.63 roughly, which is 0.05. And here we said, okay, most of the time it doesn't need to be super exact. So probably 0.06 and 0.03 would also still work. You can, if you want to be on the safe side, you can lower it a little bit, and then still get pretty good results. Roughly, in our experience, something for UHPLC, something around 0.05 is a good start point to optimize this one. Did I lose anyone? Anybody got questions up until now? So the full width half maximum, it's the width of a chromatographic peak in here, and we use it to, for example, split in between signals. So, for example, this one is a pretty nice example because we have the 294 mass to charge ratio in this scan, but we also have it back here in this scan. And of course, like from the elution profile, we can see, okay, these are definitely two different compounds. And during the processing, or like two isomers, that's not say compounds, but two different isomers. And in the processing, we want to look at them individually because they are clearly different in some way. And so MZmine needs to split the signals in between here, and to do that, the algorithm we use, it needs an approximate width of how wide a feature can be, because otherwise, instead of just splitting here, if you set it too low, the algorithm might also recognize this one here, like this little dip, also as a split between two features. I can't say from this data it is a split, or it's just like something with the ionization and it wasn't super stable. So here, this one I wouldn't focus on too much up until now, but these two you definitely want to split, and that's why what we use the full width half maximum for, because from here then we start looking for local minima between two chromatographic signals. Yeah.
Also, maybe like most of those parameters you kind of like eyeball from the raw data overview right now, and then later on you do one set of processing, you get a full table of features, and then we look at some features now, but later we have a table of like hundreds, thousands of features, and then you can also, of course, look back again and see if the full width half maximum was different, and if the MZ and retention time shifts above. Yeah, so it's kind of like just a first step of like looking into data.
Yeah, exactly. The RT tolerance intra-sample, basically, you don't need to change this. It's already pretty high here, but so it's basically used to detect isotopic signals in our feature table and to remove them afterwards, so we have less redundancy. And so 0.04 is most of the time it's adequate. You don't need to change it. And if you, for example, know, okay, these two peaks are like 1 MZ different, and they are also pretty similar as a topic difference, then you can start decreasing it. But most of the time, for most of the analysis, you can leave it with the default here. And the sample-to-sample tolerance, that's something that we looked at the beginning when we, in the raw data overview, selected multiple files from the same data set. So I'll just do that again. I check the checkbox up here to update the raw data overview, and then for me I just selected all the skin samples, and these skin samples I'll just zoom in here and find some signals along the retention time. And here we can see, okay, this one, the retention time was pretty much spot on. It didn't shift much. And in here, at a later point in retention time, it's also still pretty good. And even here, even though this signal gets a bit noisy, but still the retention time is stable. And the thing is, why we didn't narrow it down here is that this is pretty much an estimate. And later on, we have some statistics in the feature table that help you to better get a grasp of this value, because this is pretty important. This is what you use to align multiple samples together, and it might be either too high or too low depending on how stable the LC is and how complex the sample is. Because if you have really complex samples, you might get multiple compounds or multiple features with the same mass and close in retention time, or if it's not that complex, you don't have many overlaps there. Then are there any more questions to the retention or like the HPLC parameters here so far? No? Okay. Then let's go to the Orbitrap parameters. And I would say most of the time these are more stable across multiple analysis. We have the ion mode. The data that we have here was quite in positive mode, and then we have the noise thresholds. And so here for the noise thresholds, we have two choices. Either we can say, okay, we want to filter out anything that is really of low intensity, but we scale that with the scans. Or we can say, okay, we want to set an absolute intensity and cut off everything, for example, that is below 10E4 or so. So when and why would you want to change one or the other? It depends, because, for example, for Orbitraps, we have there's an ion trap before the Orbitrap, and the ion trap is filled, and it has an ideal fill state, and which means that there's a device that modulates how full we want to make that the C trap before the Orbitrap, and how full we want to make that Orbitrap. And it modulates across the chromatographic, across the chromatography. So, for example, at times where there's really low signals, so for example down here, we want to leave that gate open longer so we can get more ions in there for a longer time and reach that best fill state. And
that's also the injection time there. So in the table, you see 100 milliseconds injection time.
Yeah.
So the C-trap really waited like 100 milliseconds to accumulate ions. But the Orbitrap really measures the same number of ions, or at least aims to measure the same, let's say like 1,000 charges in each scan. Yeah, so that also why like the noise kind of like modulates with that. Yeah, so one scan basically we only have like 1 millisecond waited, and another scan we might have waited like 100 milliseconds to fill the trap. So noise is also very different there.
Yeah. So what Robin just said, so for example, if we look at a scan here where the injection time was 100 milliseconds, we could say, okay, the noise cutoff, we could set pretty low here. So what is a noise cutoff? Basically, we want to filter out something that looks like a grass in our spectrum, because that most of the time is just electronic noise that we get from the processing or from the detector. And in here, for example, in this scan, you could set this quite low because there are a lot of signals at the same intensity. That's what we want to look for. So it looks like a mown lawn. And here it would be, for example, 2000, so 2E3, because it's pretty low. But when we look at something else, so for example, when we are having a lot of ions eluting from the column. First of all, we can see here in the table that the inject time is really small, so it's just 1.3 milliseconds. And what we can also probably see is that the grass that we observed earlier now has a completely different intensity. You see, for example, here it starts to appear at 200,000 counts and not at the 3,000 that we saw before. So that's because the Orbitrap always normalizes, okay, how long was my fill time? How many ions did I observe? So you still get, nice chromatographic shapes. So what we want to say is it makes sense that for trap instruments, you don't look at an absolute noise level, but you look at the lowest intensity that you observe in the spectra. So for example, here it would be, I don't know if there's something really small in between here. It looks like it. So it's, about this one. So it's, I think 120,000. And we now want to multiply that with a given number and then process each scan individually, because only that way we can, make an adequate threshold, because otherwise, we'll either filter out too much or too few. Okay. Everybody needs another explanation? I wouldn't say it has to be the absolute lowest injection time. I would just check, okay, when in the in the base peak chromatogram, when is there like a really high signal? I could probably also select this one and do the same. And it just makes sense to go through like the extrema in your data set. So when you have really high intensity and when you have really low intensity.
So I think because it's just a spectra of noise, you know, and there's this like chemical and electronical FT noise and FT spectra. Yeah, so I think the factor is pretty much fixed. You can lower it and you can say 3 times the noise, but it's really just the lowest signal, right? The noise might be even higher than the lowest signal. So that's why we kind of give a little extra and we say 5 times the lowest signal. But that's kind of like just eyeballed because it usually works. And if you really want to go down to seeing everything, you can also not apply this denoising step. It's just going to run longer and also might produce way more features. So it's also, if you run 1,000 samples, you want to maybe increase it a little bit. And that's also why when you go to the wizard, we're going to have 2 noise levels applied, 1 to MS1 and 1 to MS2 and everything above, like MSM. Yeah, because in MS2 spectra, when we look at the spectra in the raw data overview, and maybe when you go to the table, so Stefan already selected like a scan by just clicking somewhere. And if you use the keys, actually, you can go like left and right, and that jumps from MS1 to MS1. So it kind of skips the MS2 scans. But if you use the keys and go down and up, you actually go through all the scans. And there's the MS2 scans also here. Because we enlarge it so much, and maybe you can you make this one smaller so that we can see the MS level?
Yeah,
okay.
It's hard to resize because it
resizing is broken. So but yeah, there should be the MS level here for you at least. And so then if you just go down and you see also the precursor MZ there, right? If we select a scan with a precursor MZ and zoom out on it, we're going to see that there's usually not so much noise. Like, seems like they already apply more filtering. And also, of course, we have the precursor isolation that also at least gives us more chemical, pure spectra, right? It should be just from this one isolation window. So that's why we have 2 different noise thresholds. And for the MS2, we can go lower and say, okay, we don't want to filter out so much. And for the MS1, we can go a bit higher and then speed up the whole processing for thousands of samples.
So what I want to stress again is these first steps, they are like we rather be a bit stricter. And then if you see, okay, I didn't, for example, get all my QC features, but I know they are in there, they are just less intense. then you can lower these thresholds and until you have like a satisfactory result. And otherwise you can leave it with the default. So it's always data set dependent. It's always depends on the sample, the chromatography, the instrument settings, like how clean is the instrument at the moment, and stuff like that.
Yeah, I think we're running a bit late for the break, and I hope everyone's with us. Like, we would like to finish the last 3 tabs, and they are like, there's basically no settings hidden. The worst one is UHPLC. Orbitrap is also kind of like, you have to understand the concept. And then we're going to have the break when the when the processing runs. Only takes like a minute or so, but we're going to have a quick break then.
So I guess we need like 10 more minutes at maximum or so.
Yeah, maybe.
So the the minimum feature, first of all, one more note. If you want to be a bit more specific and don't want to eyeball as much from the raw data overview, there's the old way of using MZmine, and you could go to raw data methods, mass detection, and mass detection. So if you want to open a dialog, I'll leave it open here for a second so everybody can follow along. And yeah, opening the dialog, we have some settings. And what's nice here is that for the mass detector, we can select multiple different ones. The factor of lowest is our default for trap-based data. So we select the factor of lowest at the mass detector, and then we press the setup button. And as soon as you press the setup button, you get another window, and you can select the show preview feature. And then the window gets a bit bigger. Everybody here? Was I too fast? Yeah, sure.
Mass section on the top.
So you go to raw data methods and mass detection and mass detection. Then you get this dialog here. And what's important, for testing now is that in the mass detector, you select the factor of lowest signal. There are a couple of options, but that's the one we actually want at the moment. And then we press the setup button on the right next to the factor of lowest signal. And that should open us this window, which is pretty small. And currently it just says noise factor and a text box. But down there, there's also written in italics, it says show preview. And when we select that and open it here, we have a data file selected and a scan. And then usually what I do is just I go to the middle of the of this scan selection box. So I click it and I go to the middle and I select a scan that says MS1. So there's probably just ones with long caption and ones with short caption. And I select one that has a shorter caption because these are the ones with the MS1. So this is where we do a full scan and not a data-dependent fragmentation scan. So I select one like that. And then in here, I can zoom in. In this chart, what this chart tells me is, first of all, in black, I have the spectrum. And the red dots now tell me, okay, this signal was detected by the mass detector. And if a signal doesn't have a black dot, which is a red dot, sorry, which is all the low intensity signals down here, they will be filtered out. So these are the ones that don't match the noise factor of 5. And these are filtered out for the further processing.
And this is really done for like each scan individually, right? The factor. And so you're going to see if you change to also MS2 scans, for example, or other MS1 scans, you're going to see that it's kind of the same thing, like lowest signal and then times 5.
Yeah. And let's just, I'll just get one exemplary MS2 scan. I hope it's a good example, because in here, the MS2 is not so good, so it's not a good example.
Doesn't matter.
Yeah. basically we say what we see here, okay, 5 is too much. And if we use a lower noise factor, we still get some signals in there. I know this is not the best example, but yeah, looking for a good example now in this list is probably, takes a longer time. But basically, we want to see something like this. The noise is filtered out and you still have, the more significant signals remaining.
And you can really see that like there's less of this like very noisy small signals. And also if you zoom in on those signals, again, the mask effect, you can directly see that many of those signals are just random. Yeah, so they really spray randomly with a mask effect and they don't have something reasonable.
Yeah. So, okay. This was just another way. Yeah, 1 second. This was just another way to judge the noise factor or the noise level. You can do it from the raw data overview, but yeah, this one I would say is a bit more sophisticated. And yeah, if you really want to see the results as a preview, you can use this way. And yeah, for now, yeah, we just leave the settings as they are. We can just close all these windows. And there was one question.
Yeah, can you kind of rationally come to the best fitting factor for this data set that you're looking at?
I think maybe let's have questions after the coffee break, because then you can also exchange with some of the questions and we can kind of come back refreshed. But it's definitely a good question. Yeah. There's only a few parameters really to set now.
Yeah. And yeah, the tolerances, most of the time for the instruments, if they are well calibrated and the histogram that we looked at in the beginning looked fine, you probably don't need to change them. So that's also what we're doing now. The last parameter that we are looking at here was the minimum feature height. And as you saw before, like the noise factor always, or like the noise level, if you look at it in an absolute way, it always changed throughout the scans. So currently, Robin and I are discussing if we should also change this to a factor, but for now, it's absolute. And what you can do to say, okay, this is a good value or this is a bad value. So 1E5 usually is our Orbitrap default, and our estimate is look at the chromatographic shape. So, and not look at the chromatographic shape of the most intense signal, but what I do is I just go to one compound, and then I start looking through the isotope pattern. So in here, the second isotope still looks pretty good. Then I go to the third isotope, and yeah, this one starts to have like one signal less. And probably if I can still find it at 418, that's probably one of these. Yeah, these ones are even flatter and start to have like only 3 or maybe 4 data points. So in between here is where I would want to send the cutoff for a signal minimum intensity to obtain it afterwards. So that's also reflected here. So it was between something E4 and something E5. So we say, okay, we leave it at 1E5 for the processing steps. And then we just have tolerances. As I mentioned, most of the time you don't need to touch them. They are different because the scan-to-scan tolerances is within one run, and it's like how stable a signal may be or how much it may jitter back and forth. And it's not averaged yet. So this one is usually higher than your instrument vendor suggests. So for example, Thermo says mass accuracy is like 2 ppm or so. And then what we do is we just increase that by a good number. And for the chromatogram building, for example, for Orbitraps, use 10 ppm and 0.02. And the other tolerances are then judged to use isotope patterns and to correlate in between samples. But most of the time, this is then closer to what Thermo tells you how accurate your mass is. And what you have to remind yourself here is that an instrument cannot just jitter into one direction, but also in the other. So if you have in one sample, you have 2 ppm in that direction, and the other one, you have 2 ppm in that direction, then you usually want to increase it and use a safety margin. Yeah. You can make
Maybe, yeah, let's keep the comments for after the breaks. Yeah.
Still using this thread, right? And there is software for interactive photonics that is using the samples to normalize the mass. You don't have to worry about it.
Yeah, I mean, there's many ways to normalize MZ and also recalibrate and so on, and to get like better accuracy. But yeah, like I think that's maybe for like later stage. And I definitely like during conversion and so on, there's different ways. But yeah, I think the most important step is really like those parameters. You don't have to touch much. You get a feeling for the intensity, especially because you also want to acquire MS2 spectra, and the signal needs to have some intensity to actually also acquire good MS2 spectra. And then for the next steps, it's very important that like those settings can basically stay like they are for now. And I would just change the minimum samples per line feature to 10%. Yeah, because there's like kind of like, okay, how often do you need to find the same signal, the same feature to actually do statistical analysis later on, right? I would say if you have triplicates, for example, maybe 2 out of 3, because we could also maybe miss it in feature finding. But if you just set it to 10% and we do it with 88 samples later, there's going to be like 8 samples that need to be detected. And you can increase this, especially like when you do statistical analysis of slight changes across like metabolic states. You might want to find it in more to even have statistical significance, right? So maybe just change it to 10 and keep the rest like it is. It's basically for optimization. It's optimal with the keep.
Yeah. So this is important that it is set to keep the original feature list.
Very important to keep. And then on annotation, if you have the JSON file, you can either just drag and drop the JSON file from your folder, just drag and drop it in there. Yeah, you can just leave it. Maybe it's somewhere hidden.
Okay.
Or you can click that little all JSON files. So there's this all JSON, and also there's a check mark in subfolders. So you can check this like in subfolders. And if you then do all JSON, it opens a dialog and you select the folder where all your libraries are sitting, and then it gets you like all the .json files. We can say that later, but yeah, you see I'm a messy with the libraries, so there's a lot of them. But and the JSON is a very generalized format. We're not going to talk about it now. It's a very generalized format used for many different things. So that's why they look different from GMPS and Mona and all the different tools. Yeah. But if you have that, so you drag and drop it in there, or you load it like that, we can go to DDA. And in here, the defaults are fine. Like we want to export all files that we can get. And I would encourage you also to export everything that you get, because if you process once, it's definitely nice to have, and you don't have to go back. And so the only thing that you have to do is really check this like export path, and then go on select, and go into a folder. And I already have processed, so maybe you can go create like a new folder in the summer school and do like results 2 or something. And so it's very important that you select the full path. Yeah, so it cannot be just like results and file name, but it should be full path. And so you create a new folder, go in that folder, and then also type in the file name, and go in the folder, and then in the file name, type in something like summer school or group 1 or group 2 or something. Yeah, so just give it a file name. You don't have to specify a format, because we're going to export 10 files maybe, and we're going to attach suffixes to it so that you have all the files, and we know which ones to use for series, which ones to use for GMPS, and so on. Yeah, nice. And yeah, so there should only be export annotation graphics. We don't need now, so you can just leave that unchecked. And if you have that, first thing that we're going to do is save presets. So you click the save preset, and you have a name there. So you just add like a file name, and you leave everything checked. And we save this wizard preset. The wizard preset is kind of nice because you can just stitch together different instruments. You have the like UHPLC, GC, whatever, and you just define those parameters. You export it to a wizard preset, and then you can share it. Yeah, so it could also be something like the Q executive HF, and so on. And when you did that, so you click on OK and save it, we at least have it somewhere. And then you click on Create Batch. And we're not going through all those steps, but on the right side, you now see all the different steps that we're going to apply. Yeah. And with this done, I would say we just click on OK and run. And it's just going to do its job. And some people are going to have problems because they didn't select the data files maybe, or they didn't select the library right. But then we can just go around and help you now in the copy break.
Yeah, for the
And
others.
maybe you open the task and then
Oh, yeah.
like, and now in the task, you can see how we actually exported new files because we also selected the wrong files. Not wrong. It's totally fine. Like we selected 8 other files. And now it's just going to import those 8 files and it's only going to process those 8 files. Like the other ones are not being touched right now. And maybe you can change to feature list. And we're already at step 13 of 20. And you can see how it's like producing a lot of new feature lists for each sample. And we're going to go through that after break.
Yeah, so now we can have a break and people who have questions just raise their hand and we
we're going to grab a coffee and then come around and talk.
Yeah.
And let's do the 30 minutes break. Like it was 30 minutes, right? That we ran over.